All right, welcome back. So on page 3 in your packet, we're still kind of in this, the beginning stages of hypothesis testing, getting all the details ironed out, and we saw the example about the proportion of made free throws for Mrs. Manuel in the last couple videos. We're going to take a look at an example that talks about the population mean this time, and one of the goals of this lesson is to kind of analyze the decision-making piece a little bit more and talk about like the what ifs. What if we're wrong? What does that mean? So for this example, should CV switch to bottled water? A mean lead level of 15 parts per billion is considered safe, while anything above 15 parts per billion is considered dangerous. Mr. High believes the CV water is unsafe, so he takes a random sample of 200 households. He finds the average lead level of the sample to be 16.5 parts per billion. This is giving us that preliminary evidence that maybe there's a concern here, because that is over this limit of 15 parts per billion. But could that sample result being higher have occurred purely by, or how likely is that result to have occurred purely by chance? Well, let's kind of take a look at that first. So, as always, we want to identify our population, parameter, sample, and statistic. Now, the population in context here would be CV households. We're not talking all of Lancaster County here, or all of PA. So, all CV households will be our population. The parameter would be the true average, so population mu, mean, the true average lead level. The sample would be the 200 random households that Mr. High has collected the data from. And the statistic would be the sample mean that he obtained. So X bar for sample mean, and that was 16.5 parts per billion. All right, let's start by stating the appropriate hypotheses. We always assume innocence until proven guilty. The null hypothesis is assuming that the true population mean really is 15 parts per billion. The alternative, what if it's actually more? So the population average is greater than 15 parts per billion. Now, if it's equal or even less, this would be safe. Water is okay, keep drinking, no problems. But if we find the true value to be greater than 15, well, now we have an unsafe situation. We're gonna have to act on that. So should CV switch to bottled water temporarily until the problem is fixed? I don't know. Well, let's find out. So Mr. High simulated taking 100 samples from safe water, assuming the null is true. From the dot plot, estimate the p-value for a sample mean of 16.5 parts per billion and interpret the p-value. So we've got 100 dots here. Each dot represents a sample of 200 households' average lead level if we are operating in an area where lead levels are safe. So 16.5 would be way over here. Now, based on the averages here that we have, that did not occur exactly, but the p-value is as extreme or more than what was observed. So we do have 3 dots, 3 samples out of the 100 that resulted in levels of 16.5 or greater purely by chance when we're working in an area where the lead level is actually safe. So that's about 3%. That's the p-value, the estimated p-value from this simulated sampling technique. So interpret that. Assuming the lead level is safe, there is about a 3% probability of getting a sample of 200 households to have an average, kind of running out of room there, sorry guys, of 16.5 or more purely by chance. So again, that says, assuming the lead level is safe, there is about a 3% probability of getting a sample of 200 to have an average of 16.5 or more purely by chance. That's what that estimated p-value means. Well, based on the p-value, should CV keep the current water or switch to bottled water until they, fix the issue? Well, since the p-value is less than 0.05, so 0.033% is less than 0.05, we, if I can spell that correctly, should reject the null. Remember, that was that the mean was 15 or maybe less, and it's safe. Therefore, we have convincing evidence that the mean is greater than 15 parts per billion, and CV should switch. So based on the p-value, yes, it would be a wise idea for CV to switch to bottled water. Now, what if our answer was wrong? Would there be a consequence? What kind of consequence to being wrong is there? So let's suppose the decision from above is wrong. What would be a consequence? Well, okay, the decision's wrong, meaning water actually was safe. Okay, people buy bottled water anyway. They didn't need to, so they're spending money that they didn't really need to spend. Okay, not the worst thing in the world, but lead levels are safe, is actually safe, but people start buying bottled water anyway. So, I guess I can just say, in summary, a waste of money, at least a little bit. Okay. Well, what if, let's suppose for a second, that the p-value is 0.14, 14%. What would have happened if we would have found that 14% of the time, purely by chance, a sample of 200 would produce a value that we saw purely by chance? Well, if that's not less than our 0.05 cutoff value, we would not reject the null. So 0.03 would be greater, oh, not 0.03, goodness gracious, Mrs. Manuel, that 0.14 would be greater than 0.05. So we fail to reject the null. We do not have convincing evidence that the true average is greater than 15, in other words, that the water is unsafe. We don't have convincing evidence that the water is unsafe. Let's say that is the decision that we make. Based on the sample values, let's say that occurred instead. All right, let's think what happens this time. What if this was wrong? What if we said, no worries guys, your water's still fine, all is well? What could happen? Well, people think everything's fine. They keep drinking the water that they have. Turns out the lead level was too high, and now the consequence could be illnesses, health issues. Definitely a worse scenario than just wasting a few extra bucks on some bottles of water. So in this case, if the decision is wrong, what happens? Well, they continue drinking unsafe water. And now we possibly have health issues. Definitely a worst case scenario. So this is one of the things we kind of have to weigh out. We don't want to be wrong, but we have to accept the fact that we are doing the best we can to make a conclusion based off of the sample that we have. And when we make that decision, be it reject the null hypothesis or fail to reject the null hypothesis, we have to realize that we just might not have gotten it right. So if we are wrong, we'd like to make sure that we are wrong, that we have the potential of being wrong in a sense that is the least detrimental. Well, in this case, I'd rather err on the side of caution and have people buy bottled water, even if the water were safe from the start, because a little waste of money, $5-10 on some bottles of water, is a much less concern than the health issues that could go along with having them continue drinking water that really isn't safe. So is the error made in question number 5 and number 7 more serious? Definitely number 7. The health issues far outweigh a little wasted money.